makes sense. Conjugate pairs theorem. Let f of x be a polynomial whose coefficients are real numbers. If a plus b times I is a 0, then the complex conjugate a minus b plus I is also. Now, you might say, well, why is that going to be the case? If I take a look at the quadratic formula, x is minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now, what's going to be important to us out of this is this right here. Everything on this formula remains the same, except one of them has a center sign of plus, and one of them has a center sign of minus. What's the hallmark of a conjugate? They are identical except for the center sign. That's why you have complex conjugates. And by the way, they can go through and say complex conjugate. This is also true that if one, say, plus the square root of 3 were an answer, so is 1 minus the square root of 3 for the same reason. Because they're conjugates of one another. So real numbers, the ones that got your answers that have the radicals, will come in pairs as well as the imaginary ones. Information is given about a polynomial whose coefficients are real numbers. Find the remaining zeros. Well, that's easy. Degree 3, I have zeros of x equal 4, x equal 3 plus I. How many zeros do I need? 3. Because we're dealing with degree 3. And so the missing zero is what? 3 minus I. The conjugate. Because they come in conjugate pairs. Which leads us to the next theorem, which looks bad, but it's not. It says, every complex polynomial function, f of x, of degree n greater than or equal to 1, can be factored. And by the way, if I have degree 0, that's a constant. So the polynomial f of x equal 5, that doesn't have any meaning because he doesn't have any zeros. He won't touch the x-axis. Can be factored into n linear factors not necessarily distinct of the form. Here's the leading coefficient times 1 minus the 0, 1 minus the 0, all the way down to 1 minus or x minus the 0. Well, that's what we've been doing. Because if I know the zeros, then I know the factors. And it's going to be x minus the 0, x minus the 0, x minus the 0, x minus the 0. Whatever it happens to be. So that brings into play my, and by the way, I want you to notice this too. It has that a polynomial function of degree n has exactly n zeros, not necessarily distinct. That means multiplicity. So if I have something of multiplicity 2, it's considered to be 2 zeros. Not necessarily distinct means multiplicity. So 1 comma 2 multiplicity 2 is the same as 1, 2, and 2. So here we go. Factor theorem, my favorite theorem, which means that if you know the zeros, then you know the factors. If you know the factors, then you know the zeros. And essentially where we are right now is if I know the zeros, then I know the factors. What we just completed prior is that and if I know the factors, then you'll know the zeros. So we're basically working in this area right here of finding the zeros so we can do the factors.